Hello, everybody. How is everyone? I hope everyone is doing well. So, this is me, and I welcome you in this lecture. This is lecture number 6 of chapter electricity. So, let's begin this lecture without wasting our time. So, here we are. Okay. And in this lecture, before going to the main concept, let me give you a quick idea about the difference between the series and parallel combinations. Okay. We knew about series combination and what is parallel combination. But here we will see that what is the difference between them. So basically, the series combination, if I want to calculate the combined resistance of a series circuit, then what will I do? I will simply add the resistance which are in series like this: R1 plus R2 plus R3. These resistance will be simply added. Okay. Now let's talk about what is a parallel combination. So in parallel combination, what do? We will simply add the inverse of the resistance. Okay, what is the combined resistance in case of parallel circuit? It will be 1 upon R. Here it is combined resistance. Here it is what? It is combined resistance. Combined resistance. Okay, and here in this case, this is also combined resistance, but this is the combined resistance of series circuit. I hope guys you get my point. Now let's see what happens with current in the series combination. So here in this case, in the case of series combination, the current remains same, but in parallel combination, the current remains different. Okay, the current will be different in each what? In each branch of the circuit. Now let's talk about the voltage in the series circuit. So the voltage will be simply added V1 plus V2 plus V3. Okay, it means the voltage is distributed according to the resistance of the series connections. But in the parallel connection, our voltage remains same. What remains same? The 4 voltage in each branch remains same. So I hope guys you get this point. Now let's move on to the next slide and let's talk about the heat generation. It is again very important topic. What is heat generation? So basically, before telling you this directly, I want to give you a very good example. So for that, let's move on to this slide. Here you can see that this is a bullet. This is what? This is a bullet. And this bullet is fired towards the wall. So when you fired the bullet, that time the bullet has lots of kinetic energy. Okay, it has kinetic energy because it was in motion. Okay, let me write it clearly. So this bullet has kinetic energy. But guys, what happens when it strikes with this ball? So its velocity becomes 0. As soon as it strikes this wall, its velocity becomes 0. So it means the kinetic energy will also be 0, because what is the value of kinetic energy? Half mv square. So if there is no velocity, then kinetic energy will also be 0. But we know by the energy conservation that energy is always conserved. So where this kinetic energy go? Where it has vanished. So basically it didn't vanish anywhere. This is converted into the heat energy. This will be converted into the heat energy. So you will see lots of heat after the collision of this bullet from this wall. So guys, the same thing happens with this case. In this case also, when electrons move inside a wire, it collides with the particles. Okay, it collides with the particles. So because of this collision, what happens? It generates heat. Okay, so why the heat is generated here? Because of the collision of the electrons from the particles. So I hope guys you might understand what is the heating effect of electric current. So the electron collides with particles. So this concept is also known as resistance. So we can also say that for heat generation, resistance can be the cause. Okay, so resistance can be the reason of this heat generation. And not can be, it will, and it is definitely a reason for this heat generation. So I hope guys you got my point. Now let's move on to the next slide. Okay, so here we will derive a formula for heat. What will we do? We will simply derive a formula for heat. So how can we do that? So basically guys, we know that what is a potential? Potential is basically the work done to flow 1 coulomb charges in a circuit. Okay, so how can we calculate this potential? We can easily calculate the potential by dividing it from work. So if I cross multiply this here, then it will give me W will equal to be V into Q. Now, what? Although you know the meaning of these terms, but I again write it down for you. This is potential difference. This is potential difference. And Q is charge. Q is what? Charge, or you can say electric charge. So basically guys, this work done is known as energy because work done is equal to energy. So this is also can be written as heat energy. So this H here is heat energy. And this is equal to V into Q. This will be equal to V multiplied by Q. Now guys, we know that what is electric current. So electric current is basically nothing but the charge flowing in a conductor in 1 second. Or you can say the rate of flowing of the charges in a conductor is known as current. So this is the formula. Now from this formula we can calculate the value of charge, and it will come I into T, I multiplied by T. So if I put this value directly in this formula, then I will get VIT. Okay, then what will I get? I will get VIT. Now, in the previous slide, I told you that resistance is responsible for heat generation. So basically, we need a resistance in this formula. So how can I do that? How can I add resistance? So I know by the Ohm's law that V is equals to IR. Okay, what is V? V can be written as IR. Here I is current and R is resistance. So I can simply put this value in this formula here. So it will give me I square RT. So this is very, very important formula. You can mark a star here. This is very important formula. Okay. Now let's move on to the next slide. So in this slide, we will discuss that how to design a heating coil. What we will discuss? We will discuss that how to design a heating coil. So basically guys, we know that H is equals to I square RT. Now we just did its derivation and we know how did we get this formula. So basically this is known as the Joule's law of heating. Okay, this was identified by Joule. So that's why this is known as Joule's law of heating. I hope guys you get this point. Now, let me write this formula again. So H is equals to I square RT. So basically guys, here you can see that our heat generation is dependent on the square of the current. I can write it like this. It is basically dependent on the current square of the current. Now, it is also dependent on the resistance. You can see it is also dependent on the resistance, and it will also be dependent on the time for which current is passed. So these are the things on which a heat is dependent, or you can say generated heat in a conductor is dependent. Now let's move on to the next slide and let's try to understand how can we design a heating coil. So basically, if I want to make a coil or make something which produces lots of heat, then how can I do that? So because we know that the heat generated is proportional to the current in the circuit. So if I increase the current, then heat generation will also be increased. Okay. Now other thing which can be done is resistance. If I increase resistance, then also a heat generated will be higher. Okay. So now guys, let's see that how can we increase the resistance. So we can do it by increasing the resistivity, because we know that resistance is proportional to the rho L by A. And basically it is not also proportional, it is equal to rho L by A. Now, if I increase this rho, which is what? Which is resistivity. Which is what? Resistivity. So if I increase the resistivity, then our resistance will automatically be increased. So that's why to make a heating coil, I will take a wire which resistivity is higher, so that my resistance will be higher, and because of the resistance, because of the high resistance, the heat generated will also be high. Now, the other thing is a resistance is also proportional to the length. A resistance is also proportional to the length. So if I increase the length of the wire, then also our resistance will be increased and the heat generated will be increased. Now, other thing is we also know that resistance is inversely proportional to the area. Resistance is what? It is inversely proportional to the area. So if I decrease the area, then resistance will increase. And if I increase the area, that our resistance will decrease. So I need high resistance here. So that's why what will I do? I will simply decrease this area, and because of the decreasing of the area, resistance will be increased. So if I want more heat, then I will have to do these three things. Okay, first I can do it by increasing the resistivity, I can do it by increasing the length, and I also can do it by decreasing the area. Okay, guys, I hope you get my point. Now let's move on to the next slide and let's talk about the things which we notice while making an heating coil. So basically, this is the first thing that we know that if I increase the resistivity, then my heat will be higher. So to increase resistivity, what would I do? I use alloy as a metal. I use alloy as a conductor. You can say as a conductor. So basically, what is alloy? You might be thinking. So alloy is the combination of two or more metals. So alloy is what? Alloy is made up of two or more metals. Alloy is a mixture of metals. So when you mix metal, what happens? The resistivity is increased. So to increase the resistivity, I am using alloy, okay, as a conductor. Now, other thing also we know that resistance is also proportional to the L. Resistance is proportional to the L or length. So basically, if I increase the length, okay, of the wire, then also my resistance is increased. So that's why to make a heating coil, I use a wire which has higher resistance. Which has what? Which has higher resistance. I hope guys you get my point. Now let's see that our resistance is also inversely proportional to the area. Resistance is what? It is inversely proportional to the area. So basically, if I decrease the area here, if I decrease the area, then my resistance will be higher. So that's why you can see here that I am using a wire which area is very, very less. So that's why because of the less area, my resistance will be higher and the heat will be generated more. So I hope guys you understand this concept. Now, after understanding this, let's talk about electric iron. Okay, what do we need to discuss? We will discuss electric iron. So what happens in an electric iron? Why do we use electric iron? Why do we use electric iron? So basically, we use electric iron to iron our clothes. This is a very, very basic question, which we all know the answer of this question. So now let's talk about the mechanism inside an electric iron. Okay, we will talk about the mechanism inside an electric iron. So what happens in electric iron? We use a wire of nichrome. We use a wire of nichrome. Now, why do we use this wire? Because this has high resistivity. So because it has high resistivity, then when I pass current through this wire, it will generate more heat. It will generate what? It will generate more heat. And because it generates more heat, then my clothes will be ironed perfectly. So now, this is what? This is a plate. And this is made up of mica. This is made up of mica. Now, what is the property of mica? The mica is a material which can, or you can say, which lets the heat pass across it, but which stops current to pass across it. Okay, so what happens when, let's suppose this is mica. So if you are passing current inside it, then it will resist it. Okay, but if you are passing heat inside it, then it will not resist it. It will let the heat pass inside it. So basically, why do we use mica? Because in this nichrome, we are flowing some current. Okay, we are flowing some current. So we want that this current should not touch this sheet. Otherwise, what happens? When you iron clothes, then you will also get shock. You will also get shock of current. So that's why, to prevent this thing happening, what do? We will simply protect it by this layer mica. So this mica doesn't let the current pass across it, but it will let the heat pass inside it, and the heat will be transferred here and your clothes will be ironed perfectly. So I hope guys you understand the mechanism of electric iron. Now let's move on to the next slide and let's talk about the things which we do while making an electric iron. So basically, this is an electric iron. So here, as you can see, that length is higher. The length of this wire is higher. Okay, but the area here is less. So that our resistivity, or you can say our resistance, will be higher. Now to increase the resistivity, I used nichrome as alloy, and this sheet is made up of mica. And why this is made up of mica? Because I need it to be like this. Okay, because I need the current to not be transferred, but I need heat to be transferred. So that's why I use this mica, because it has these properties. Now guys, after understanding this, let's move on to the next slide and let's talk about electric power. Okay, let's talk about electric power, which is a very, very important thing in this chapter. So guys, what happens? This is the formula of electric power. It is work done per unit. It is what? Work done per unit. So what is work done? We know that this is a work done. Why? Because when I told you and when I explained the potential difference, then I told you that potential difference is the work done to flow 1 Coulomb charge in a circuit. Okay, so this was the formula. Now, if you simply cross multiply it here, then this will give you this formula. And what you can do, you can simply replace this Q by I into T, because we know that I is equals to Q by T. This is equals to Q by T. So this will be VIT. Now, if I put the value of V as IR, because we know by Ohm's law. This is we know by Ohm's law. So I can simply put this value here, and this will give me W is equals to I square RT. Okay, this will give me W is equals to I square RT. Now, if I replace I from here, then I can also write V upon R. This is also I wrote by the Ohm's law. By the Ohm's law. So basically, this can also be written as V square T by R. If I replace this here, then it will give me this formula. Now, what is a power? So power is basically nothing but energy per unit time. Or you can say the energy consumed per unit time. At here, the energy is equal to the work done. Okay, energy is equals to the work done. So I can also write it W by T, and W is also can be written energy, because W is, you can say W is equal to energy. Work done is equal to energy. So the formula of P is E by T. Okay, I hope guys you get my point. Now, we know that, okay, let me change the pen. We know that this P is equals to W upon T, okay, or you can say E upon T, and this W can be written as VIT, okay. and here you will write T, and T, this T will cancel this T, and we will get this VI. So P will equal to be V multiplied by I. It means V is potential difference, V is potential difference, and here the I is current. So this is the first formula of power. Now this is another formula of power, and this is P is equals to I square R. P is what? I square R. Now, how did I calculate this? This is also very simple. Just simply replace this value of V, and we know V is equals to IR by Ohm's law. And if I put this value in this formula, then it will give me this formula. Now, again, I can also replace this I by V upon R. And if I replace this I by V upon R, then it will give me V square by R. So this will be my third formula. So I hope guys you get my point. This is formula number first. This is formula number second. This is formula number third. And you can use these formula according to your convenience. Okay. Now guys, let's talk about what is the SI unit of power. So SI unit of power is watt. Okay, what is SI unit of power? The SI unit of power is watt. Now let's move on to the next slide. And let's talk about some other units of power. So basically, there are some other units of power as well. So the commercial unit of power, let me discuss first the commercial unit of power. So commercial unit of power is kilowatt hour. What is kilowatt hour? So what does this kilowatt hour mean? So kilowatt hour means that how many energy do we consume? How many energy do we consume in 1 hour? Okay, and here the energy consumed will be in kilowatt. Will be in kilowatt. You have to convert it in kilowatt. Now this is also another unit of power, and it is horsepower. And 1 horsepower is equal to 746 watt. So this is an additional information. You can remember this point also, that 1 horsepower is equals to 746 watt. Now guys, let's move on to the next slide, and let's talk about the commercial unit of electrical energy, or you can say the electrical power. Okay, so how can we calculate it? We know that power is written as E upon T. Okay, now you can also cross multiply this T here, then our energy will equals to P multiplied by T. Okay, because we saw that power is energy upon time or work upon time. Okay, we saw these formulas in our previous slide. So this work done can be written as energy, and if you cross multiply it here, then it will give you E is equals to P multiplied by T. P multiplied by what? T. Okay. So now guys, what will happen, that this 1 kilowatt hour, this 1 kilowatt hour is the unit of electrical energy, and this is a commercial unit. And how can I write it? Because here we took power in kilowatt hour, and this time is taken in what hour? This time is taken in hour, and this is taken in kilowatt. Okay, now let's calculate the value of kilowatt hour in joule. Okay, so how can I calculate it? Basically, we know that this 1 kilo is equals to 1000 watt. Okay, and this 1 hour can be written, this 1 hour can be written 16 minutes. And if I multiply further with 60, then it will give me seconds in 1 hour. Because in 1 hour, how many seconds? 60 into 60 seconds. So I simply put this value, and if I solve this, then this will give me 3.6 into 10 to the power 6 and joule. This is the value of 1 kilowatt hour in joule. Okay, this is the value of 1 kilowatt hour in joule. So I hope guys you get this point. Now again, let's move on to the next slide and let's talk about some symbols of the components. Okay, so basically, this is the first symbol, and it is a symbol of electric cell. This is a symbol of what? This is a symbol of electric cell. And this is combination of cells. This is combination of cell. Let's suppose this is cell number first, this is second, this is third. So this is a combination of cell. Let's move on. Okay. So here, this is a plug key or switch. This is a plug key or switch. And this is also a symbol of switch, but in the open case. Here in this case, a switch is open. Okay. So these are some symbols. Now, this is the symbol of a joint wire. This is a symbol of what? Joint wire. And this is a symbol of a wire crossing without joining. Okay, let's suppose this is a wire, and if I simply make a wire cross over it without joining it, this is not a join. The wire is above this wire. Okay, this upper wire is above this lower wire. But in this case, the wire is getting connected. These wires are connected to each other. So I hope you get it. Let's move ahead. Let's talk about electric bulb. So basically, this is an electric bulb. This is an electric bulb. And this is a symbol. Whenever you use bulb in circuit, then you have to show it by this symbol. And this is resistance. This is what? This is resistance. So basically, the symbol of resistance, although we had discussed these symbols when we discussed in individually, but to memorize these symbols, I am showing you here. Okay. So this is the symbol of resistance. It is like a speed breaker. Now let's move on to the next slide. Now, this is also a symbol of resistance. This is also a symbol of resistance. But you might confuse, then what is the difference between this symbol and those symbols? So this is the symbol of a variable resistance. This is the symbol of variable resistance. Here in this case, the resistance will vary. Okay. So that's why its symbol is different from the previous symbol. Now let's talk about symbol of ammeter. So this is a symbol of ammeter. Okay guys, I hope you get my point. Now let's move ahead. And basically guys, at last, we will discuss the symbol of a voltmeter, and it will be like this, a circle, and in this circle, there will be a voltage. Okay. And these are another formulas. This formula number first is Q by T. So here, this Q is our charge and this T is our time. Okay. And in this formula, here V is potential difference. Potential difference. And this W is work done. And this is Q, which is a charge. Okay, guys, I hope you get my point. Let's move on to the next slide. And let's talk about the potential, and that is V. And the value of V will be IR. This is our Ohm's law. and this is Q, and its value is Q is equals to NE. Okay, and this is the formula of resistance. R is equals to R1 plus R2 plus R3. We had discussed all these things. Okay, but here I just want to show you that these formulas are to be remembered. Okay, so for your help, I just put it here. So this is again a formula of resistance. So according to this formula, R is equals to this resistivity into L upon A. And these are the formulas of heat generated. First formula is H is equals to VIT. Second formula is H is equals to I square IT. Third formula is H is equals to V square T by R. So I hope guys you might understand this chapter and this lecture.